everyone. My name is Steve Hale. I'm a Senior Engineering Manager here at CAE Associates. Today I'm going to talk about how we can get our nonlinear analysis to converge, and this is a very common problem, especially for people who are first starting out with running nonlinear FEA problems. The presentation will last approximately 30 to 40 minutes. Everyone is muted, so if you do have any questions, just type them into the chat window, and I'll try to address those at the end of the presentation. Okay. I just want to give a little background on our company. We are CAE Associates. We're an engineering consulting firm here in Middlebury, Connecticut, and we specialize in both structural and CFD analysis. We've been an ANSYS channel partner since 1985. This presentation is part of our ANSYS e-learning series, which we give about once every month on a variety of different topics that we believe will be helpful for ANSYS, the ANSYS community, and our customers. In terms of our website, it's caeai.com. I know that's a mouthful, but if you go to that site, there are quite a few resources there that can be quite helpful. One of them is our resource library. It has links to update seminars that we've given in the past for each new revision of ANSYS. Case studies. We've written quite a few different case studies on different consulting projects that we've done, and a variety of ANSYS presentations. Another excellent resource is our Engineering Advantage blog, which you can access from our website. And we put those out once a week on a variety of different topics, ranging from CFD to structural analysis, some of them very general and some of them more specific. We also have an easier training registration calendar, so you can register for training there, and there's a CAE University link that you can look into, and that will give you some guidance on what classes you could take to that are best for your application. Okay, the ANSYS e-learning presentations have all been recorded, and you can access those either directly from our website or you can go to our YouTube channel, and there's the link to our YouTube channel right there. And this one will be recorded and posted very soon as well. Okay, let's move on to the nonlinear convergence topics. First, I'm going to talk about nonlinear analysis, what it is, and what is convergence, what causes convergence, how we obtain convergence, and the primary causes of non-convergence. And then I'll go through a demonstration problem. There are three major types of nonlinear analysis. The first one is geometric nonlinearities, and this one really includes three subclasses of nonlinearities. Large deformations, some people call it large rotations, also large strains, and stress stiffening. And what happens here is the direction of the load vector can change throughout the analysis. The stiffness matrices need to be updated during the analysis. Also, as the elements deform, those stiffness matrices have to be updated. You can get both a stiffening and a softening response depending on the type of geometric nonlinearity that's occurring in the analysis. Now, the good news there is that it's very easy to activate those nonlinear effects. The second one is material nonlinearities, and there are a number of different types of material nonlinearities. Probably the most common one is metal plasticity, but some of the other ones you can have are, say, viscoplasticity, viscoelasticity. Creep is not an uncommon one, and hyperelasticity, which is used for rubber-like materials and some plastics as well. In metal plasticity, for example, you have a nonlinear response because once you reach that yield point, the material softens. And that curve, that graph that you see on the right, shows the stress strain curve for just a very simple metal. The last one is probably the most difficult one to solve for, and that's contact nonlinearity. It's also known as a changing status type nonlinearity. And the way that FEA codes handle this is when two parts come into contact with each other, it activates additional stiffness. And that's a very high stiffness that suddenly gets activated in the stiffness matrix. And that can cause some serious convergence problems in many cases. Now, ANSYS uses a Newton-Rapson algorithm to obtain a converged solution. So what it's doing here is it's trying to balance the internal forces inside the structure with the applied external loads. And because the equations are solved using linear equations, it has to constantly update the tangent stiffness matrix as it's solving. So it has to go through a series of iterations, and you'll see this in the graph on the right. As it solves, it's constantly updating that KT stiffness matrix until the applied forces are balanced by the internal forces. That's the F and R vector. So those iterations continue. Now, typically, if you have a very smooth force deflection response, then the Newton-Rapson algorithm does a very good job and it can handle it without much in the way of modifications. However, when you have contact, or if you have a softening followed by a stiffening response, it can become quite difficult to obtain a converged solution. So let's look at the primary causes of non-convergence. The first one is excessively low stiffness. If you have a full section of a part, a very large section of a part that becomes plastic, if it goes to plastic regime, the stiffness terms become very low. The material becomes very soft, and then that dramatic change in stiffness causes convergence problems. Buckling or other structural instability, that compressive stress causes the overall stiffness of the structure to decrease dramatically. If the stiffness changes abruptly, that can cause problems. If bodies suddenly come into contact with each other, if the contact stiffness is too high, that typically occurs when you have flexible structures. Like if you have beams that are cantilevered out, or if you have plates or shells that are loose and unconstrained, and they come into contact with another part, what happens there is that when they come into contact, that contact force can effectively push them off the surface. Then the internal stresses can cause that part to then bounce back and hit the surface again, and that's a contact shattering type of problem. And you will see the force convergence history oscillate in that case. Severe element distortion, that's another common problem. That can occur when you have contact at sharp corners, so it can be helpful to round out those corners, put in chamfers or blends. Or if you have extreme nonlinear material deformations, those can be caused by plasticity or hyperelasticity, for example. Rigid body motion is another typical problem. Usually you run into that when you have a contact analysis and you have a gap between contacting bodies. If there aren't enough constraints applied, that can cause an issue. Contacted bodies, again, that start off in open configuration, that can cause a problem. Also, if you have, say, a pin in a hole and you don't have any friction, that pin can then spin in that hole, or a bolt in a hole. So that could be a nonlinear rigid body motion problem. All right, let me ask you a question here before we go into the demo. What model property causes you the most convergence problems? Is it contact, plasticity, creep, buckling, large deformations and strains, or some other type of behavior that's causing your convergence problems? So I'll just give you about a minute to think about that and answer that question, and then then we'll move on to the demonstration. Okay, hopefully everybody's had a chance to answer that. So let's take a quick look at the results. Okay, so it looks to me, with a few exceptions, the majority of you have responded that contact is the model property that causes you the most convergence problems. And that's understandable because that is a highly nonlinear behavior. There are issues with sliding. There are issues with initial contact gaps. And we'll talk about this more when we get into the demonstration problem because that problem includes both plasticity and contact. All right. So here's the demonstration problem. We have a punch penetration, essentially a steel punch penetrating a relatively soft material that includes some plasticity. Okay, we have an initial hole. This is the deformed shape here on the right, and this is the cross-sectional view. For the purposes of this demonstration, it's run as an axisymmetric analysis. All right, so let me bring that up here. So here's the geometry, an axisymmetric model with the axis being the y-axis up the inside or left edge of this punch. The punch is structural steel, and then you have a softer material that represents the plate. What I'll do is I'll just open up the engineering data page, and we'll take a quick look at that. This plate material has a relatively low elastic modulus of 1 million psi, yield point of 20,000 psi, and then a very soft post-yield stiffness as well. And that's called the tangent modulus, and that's 10,000 psi. All right. Now I want to look at a couple of features of this model. Let's take a look at the contact interface first. We have frictional contact between the punch and the plate. It's a little hard to see here. Let's look in. We have these edges, or the target surface on the punch, and then we have the contact surface is over here on the plate, representing these edges here. This one and the blend at the corner. Now, one thing to notice here is we have a very high friction coefficient of 0.4. Okay. Large deflection effects. So if I look under analysis settings, you see large deflection is turned on. What this means is that I've activated the geometric nonlinearities so that they will now be accounted for during the analysis. Anytime you get any type of rotation in the structure of, say, 5 degrees or more, or strains in the structure of more than a few percent, then you should always activate large deflections. Sometimes it's difficult to tell whether or not that's going to have an effect. If you do have any doubt, you need to turn that on, because in many cases, large deflection effects can have a significant effect on the final solution. So that's all you really have to do. Turn this on to activate geometric nonlinearity effects. Okay. The other thing I forgot to mention is if I look under geometry, the 2D behavior is set to axisymmetric. All right, so let's run the first analysis. I have a very coarse mesh on the structure. I have a fixed support at the outer diameter of the plate, and I have a force applied to the top edge of the punch of 300 pounds, and that represents the full force around the full force on the entire punch, 360-degree structure of that punch. Okay, and this is all solved in a single load step. So let me try to solve this. And it runs quite quickly because it's an axisymmetric analysis, even though it's nonlinear. And what you know is what you'll notice is that you do get a solution, but the displacement, so this is total deformation, is an extremely high number. All right, so it tells me that that punch was not properly constrained by the contact surface there. The other way we can check this is I could turn off the weak springs. So I turn off the weak springs and resolve it. What you'll see is you'll see a new message down in the message window that says an internal solution magnitude limit was exceeded. That means we have rigid body motion in the punch. So we need to prevent that from happening. One thing you should always do in a nonlinear analysis, you should always try to use more than one substep so you can ramp on the load more slowly. So what I'm going to do here, I'm actually going to solve this a little differently. I'm going to use two steps. In that first step, I'm going to apply a very small force of 1 pound. The second step, I'm going to apply my full 300-pound force to the punch. I'm thinking that that 1 pound force might be able to push it into contact. So let's see what happens there. So now I'm running it as a two-step analysis, 2 steps. First step, 1 pound. Second step, 300 pounds. So let's solve that. And again, we get an internal solution magnitude limit exceeded. So that again tells me that we have rigid body motion. All right. What you'll notice here is we have a gap between, a starting gap between the two parts, between the punch and the plate. So the way I can check for this, if I have a complicated model, it might be difficult to find these gaps. So I can find these more easily if I go to Connections, Insert, Contact Tool, and I can get some initial information about each of my contact pairs. So I generate initial contact results. And it has to run through some calculations to check for the initial contact status. If I see anything other than gray or white, what it means is that we have an open contact condition. So we have an open contact condition at that contact pair, and this is the gap. So I have two options. I can either take that punch and move it by this amount to close that gap. So I could go back to Design Modeler or my CAD program. I could move the part. Or another thing I can do here, I can use a trick. Under my contact settings, I can go down to the interface treatment under geometric modification, and I can change this to adjust to touch. Now, effectively what this is going to do is going to take my contact surface and offset it by the minimum gap size to close that gap between the two parts. The other thing I should do, you should always do this in a nonlinear analysis, is you should use more than one substep. All right, now for my first step, I don't really have to do it because I have a very small force applied. Now, my second step, I'm applying an additional 299 pounds, so I'd like to use multiple substeps, which will then ramp on the force. Instead of applying all that force in one step, it's going to use multiple substeps to ramp on that force. So to do that, I go to Analysis Settings, change my step number to 2. I'm going to turn on Automatic Time Stepping, and then I have Initial Substeps, Min Substeps, and Max Substeps. And what this is going to do is it will use initially 20 substeps to ramp on that force of 300 pounds. If it converges rapidly, it could use fewer substeps. So I could actually make this a smaller number, let's say 10, and then if it converges rapidly, it will then enlarge the size of each subsequent substep and until it reaches a minimum number of substeps of 10. If it has difficulty converging, the automatic time stepper will then use more substeps. So it's good to use a range of substeps here. The initial substeps is the starting size of each substep. So it's going to take my 300 pounds, subdivide that load into 20 substeps. And I also now have this option that I changed just a touch to close that initial gap. I can then generate initial contact results, and now if I look at the results there, I have a nice white row of information. Number of contacting elements is 1. The initial penetration is a tiny number. There's no gap anymore. So the initial, or the Adjust to Touch option effectively closed that gap. So now let me try and run it. While it's running, I can look at the force convergence behavior. So under Solution Output, I can set this to force convergence. This purple line is the difference between the applied force and the internal force. The idea is that once this purple line gets below the light blue line is the convergence tolerance number. It needs to get below that number to have a converged substep. Each of these dashed green lines represents a converged substep. Okay. So now, if I look down at the bottom, it was able to converge up to just over 80% of that second load step. Now, what happened? Let's take a look. If I look down under the error, under the messages, it says the solver engine was unable to converge. So that's not very helpful, right? It doesn't give us a lot of information. To get more information, I can switch from the force convergence graph to solver output, go down to the bottom, and look at the messages. This message down here says element 245 has become highly distorted. So this is a element distortion error. All right. I can look at the results, and this is for the unconverged solution. That looks horrible, right? Severely, severely distorted element. I could look at the element solution prior to that. So I could pick that last converged point, retrieve that result. That actually looks fine. Okay. Let's see here. How are we going to overcome this? Well, one thing we can do, if I look at the initial mesh, this element at the corner, there's a single element in there, right? And the blend itself has 2 sides to it. It's not a very good element in the contact zone. So what I'm going to do is I'm going to change that mesh. I'm going to activate or unsuppress this edge sizing. This edge sizing specifies 5 elements around that blend. Regenerate the mesh there. And now I'm going to resolve. Now before I resolve, let me just do one thing here. You see this Newton-Rapson residual? I'm going to put a number in here, in this case 1, and what that's going to allow me to do is it's going to allow me to plot, create a fringe plot or contour plot of the force imbalance in the mesh. And that's going to be important if it doesn't converge. So let's solve this again. And I can look at the force convergence behavior while it's running here. It's moving along. I need this time point to get up to a value of 2 because the second load step by default has a time value of 2 associated with it. Okay, and it gets up to the converged point, so that's great. So all I had to do there was modify the mesh in the contact zone. I can look at the total deformation. Let me look at the final time point here. So that's the total deformation and the equivalent plastic strain. So we have a very high plastic strain level in here. Okay. Let's do something else here. I want to check. Okay. That looks fine. So let me now see if we can push this punch further down. So I'm going to change that second step to 400 pounds. And I'm going to try and resolve it. Now these red lines here in the force convergence history plot, what these represent are bisection points. This means that at this substep, it had so much difficulty converging that it actually subdivided that substep in half. And at that point, it's able to ramp up the load further. Okay, and the automatic time stepper takes care of all that for you. All right, so once again, we have a non-convergence problem. And so we'll take a look at a couple things. I can look at the Newton-Rapson residual force. There's a Newton-Rapson very high residual force right there on the other side of the chamfer. The other thing I can do is I can look at the solution output. So I switch force convergence to solver output. I'm going to go down to the bottom. And again, we have an element distortion error. Element 225 has become highly distorted. All right, so what are we going to do about this? Well, one thing I noticed when I set up my contacts, I didn't extend this contact edge around the top side of the plate. So what I should do is I should change my contact surface so that it extends over to the top of the plate. So I add that additional edge. Another thing that will help in a contact analysis, this is especially an issue when you have softening behavior. So we have a lot of plasticity that's occurring at this chamfer location. So the material is softening quite a bit. To help this to converge, we can change this normal stiffness value. So I can change it from program control to manual. Let's see, manual. And then normal stiffness factor by default will be set to 1. If we change this to 0.1, that's going to soften the contact stiffness at that location. Again, that's going to be important when you have contact between flexible bodies or contact in a location where you have plasticity or some other material softening behavior. All right, now I rerun it. And we'll look at the force convergence history again. Looks pretty similar in the beginning. gets about to 72%, 79% of that second step. Struggles 92%. And it doesn't quite make it. Okay, again, so we can look at the solver output. Again, we have a distorted element. Looks like the exact same element. I can look at the residual force. It looks pretty similar. Now, what this is really telling you, I wouldn't worry about the value of the force, but it gives you an idea of the location that's causing the convergence problem. So this part of the contact pair, this region of the contact zone is causing that convergence problem. So one of the things we can do here is we can change the contact formulation, the contact algorithm. So by default, it uses an augmented Lagrange method, which is generally the place that you want to start. It's generally the most robust and the best combination of contact stiffness and accuracy. There are a couple other options here. One of them that's worth trying is the normal Lagrange algorithm. This prevents any penetration between the interfaces and uses the contact pressure to enforce contact compatibility. So this is certainly worth trying in these types of problems. So now I'll resolve it. And I'll switch this back over to force convergence. And we'll see what happens. So we get to 50%, 60%, 73%. You can see it's struggling to converge. We have a lot of equilibrium iterations. And then finally, it does eventually converge. So this is our converged solution. Now, one thing you'll notice, which is kind of interesting, is we do have what appears to be a permanent gap in there. And that's because we changed this contact method to an adjust to touch. So it offset that contact interface by the gap value. So you will always see that what appears to be a geometric gap between those two interfaces. If you don't want that, you're going to have to manually move the two parts into contact initially. Equivalent plastic strain. Okay, so there were a number of things we did to obtain a converged solution there. One thing I should mention, if we want to push that that punch further through so that it reaches this outer edge of the punch, you would actually have to change this from a force load to a displacement load. The reason for that is because if you continue to apply an additional forces to this, eventually what's going to happen is the entire section will push through. The entire punch will push through, and there will be nothing to restrain it once the entire section reaches the outer diameter of this punch. So you would have to switch over to a displacement and force load. Okay, so we used more substeps to help us obtain convergence. We closed the contact gap using the adjust to touch option. We refined the mesh in the contact zone. We reduced the contact stiffness. That helps when we have softening behavior. We modified the contact interface by adding that edge at the top of the plate to the contact pair, and we switched over to a normal Lagrange formulation. All right, so let me go back to the presentation. I just want to wrap up here. So convergence problems, they can often be overcome using the following methods. We can add substeps. That's something you should always try. So you turn on the automatic time stepper, add additional substeps to slowly ramp on the loads. We can ensure that there are no initial gaps at contact interfaces. That helps to prevent rigid body motion. We can remove sharp corners in contact regions by adding blends or fillets. We can reduce contact stiffness in regions that experience softening or structural flexibility. We can adjust or refine the mesh to minimize element distortions and improve contact pressure distribution. We want to have, it's better to have more elements that are in contact with each other rather than fewer elements. And we can also try another contact algorithm. Instead of the standard augmented Lagrange, we can switch over to normal Lagrange, or there's another option, which is projection-based contact, that you can try, and that's often helpful as well.